Today we're going to be talking about writing the equation from a graph of a polynomial, and we're going to take a polynomial and graph the equation, graph it from the equation. Notice these are on factored forms. Later on we're going to learn how to factor equations that are larger than a quadratic. But today we're going to take a graph and write the polynomial. To do that, you'll need to note how the line is touching the x-axis. Is it crossing it linearly? Is it bouncing off? Or notice here how it kind of zigzags as it crosses. Those tell us the multiplicity of the zero. What do I mean by that? This will have see how this bounces like a quadratic equation? That's going to have a second power on that factor. And see how this one zigzags like a cubic function? That one's going to have a third power. So let's start with this first graph. Let's first find the zeros. Notice at -1, 2, 3, it crosses the x-axis. It also crosses the x-axis linearly at 0, and it bounces off the x-axis here at 3. So we're going to rewrite those as factors of a polynomial. X minus 3 comes from a factor of x plus 3. And 0 comes from a factor of x. And 3, the 0 of 3, comes from a factor of x minus 3. And again, because that's bouncing off the x-axis, we're going to put a 2. Its multiplicity is 2. How do we get this -3 to a +3, the 0 to an x, and the 3 to a -3? Remember, if we solve this factor, x minus 3 equals 0, we get the 0 of 3. And if we solve x plus 3 equals 0, we get the 0 of -3. And if we solve x equal to 0, we get 0. So we're kind of working backwards. Here we have the zeros, and now we're writing the factors. We want to make sure that we have the right leading coefficient, or the right compression or stretch for the graph. So we need to look on the graph for a nice point to help determine our compression or stretch. Here is a nice point. This is the point 4, 1. So I'm going to add to this equation an a out front, a multiplied factor, and a y. And I'm going to solve for that multiplied factor. I saw that my graph goes through 4, 1, so I'm going to replace every x with 4 and every y with 1. So that's 1 equals a times 4. 4 plus 3 is 7. 4 minus 3 is 1. So here I have 1 equals a times 28. And if I solve that, I get a equals 1 over 28. Now I'm going to rewrite this equation with the a plugged in. Y equals 1 over 28 x times x plus 3 times x minus 3 squared. And we have our polynomial to the least degree that goes through these zeros and goes through this point. Now let's do the second graph. See how it zigzags through there again? That's a third multiplicity of 3, 0. So at -1, 2, 3, we have multiplicity of 3. At 1, we have multiplicity of 1. And 1, 2, 3, 4, 5. At 5, we also have a multiplicity of 1. Straight line, zigzag. That's how I know. That's x plus 3 cubed, x minus 1, and x minus 5. now we're going to make sure we have the right stretch or compression. So I'm going to add an A to the front. Actually, I'm multiplying an A to the front, placing an A on the front. And I'm going to replace, see, I got to find a point. Here is a nice point. Over 0, down 2. So 0, negative 2. That's x is 0 and y is negative 2. So I'm going to replace y with negative 2, replace x with 0. So I get 3, negative 1, negative 5. Just replacing each of those x's with 0. And I get, oh, don't forget to bring down that third power. I've got 3 cubed times negative 1 times negative 5. So I have negative 2 equals 3 times 3 times 3 is 27 times 5. 20 times 5 is 100. 7 times 5 is 35. So that is 135. Then I am going to divide that 135 on both sides. So A equals negative 2 over 135. And then I rewrite this equation right here, replacing the A with that number. So we have y equals negative 2 over 135 times x plus 3 times x minus 1, don't forget that cubed, and x minus 5. That was a cubed on the x plus 3. So there we now have a polynomial of the least degree that has these zeros and goes through that point. Okay. Next we have an equation, and we are asked to graph the equation. Hopefully you can read that. If not, I'll read it to you. It's f of x equals negative 3x times x plus 2 cubed times x minus 4. To graph this, we're just going to sketch a graph. It's not going to be perfect. Our stretch and compression might not be exact, but we will work on that a little bit. Okay, so our zeros are at 0. That's multiplicity of 1, so it's going to cross linearly. Here's 1 at x plus 2. If we solve that, we get a negative 2. 1, 2. Almost did that at 3. Okay, there's 1 at negative 2. That's going to be a multiplicity of 3. So we'll have to cross that one zigzag-ish. And x minus 4 will give us a 0 at 4. So here is our third 0. So we have 1 at negative 2, 0, and 4. And those two are linearly. If we look at the overall degree of the polynomial, there's a first 1 plus 3, that's 4, 5. It's a 5th degree polynomial, and it's negative. That means its end behavior will start up and end down. So if we know that it will start up, then we can expect something like this over here, and end down, we can expect something like this over here, going down. So we know it's going to be going into this point from above. So we can like go out to negative 3, plug that in, and see what we're going to get for a y value to kind of just get a starting point. So negative 3 plugged into this. Wishing I had a calculator right here. So I'm going to get a pencil. 3 times negative 3 plus 2 is negative 1. That's cubed. Negative 3 minus 4 is negative 7. So here, this is going to be negative, that's going to be negative, that's going to be positive. This isn't looking, let's see. Oh, that's negative. Alright, I knew it should have been up, so I'm glad that these 4 negatives are going to make it positive. That's the way it should be. That's good. This is a 1, so I've got 3 times 3 is 9, times 7 is 63. Woo! That is up there. Up there. I don't know exactly where. My graph doesn't go that far. So I'm wishing I had pencil. I don't need that. I need it more like this. And it's going to zigzag into here. Let's see what it's doing at -1. So I'm going to plug in -1, -3 times -1. -1 plus 2 is 1 cubed. And -1 minus 1 is -5. Negative times negative is positive, times negative is negative, so it's going to be -15. That is way down there. So this is kind of... -2 had the cubic go through, so it's going to go like super fast down. But by the time, so it's going to come back up. So I'm not going to go down low enough on this graph. It's going to come back up and go through this somewhat linearly. Let's see what's going on at 1. -3 times 1. See, this is x equals -3. This is at x equals -1. Now I want to know what x is doing at 1. So -3 times 1 times 3 cubed. And 1 minus 4 is -3. Alright. Should be positive. Double check. Negative times negative is positive. Yep, it's positive. 3 to the 5th power. So this is 81 times 3. 243. So again, way up there. This is going to go up really high, back down. This is continuous. It will go on up higher. I just don't have room for that on my graph. And then I'm guessing if we were to plug in 1, 2, 3, 4, 5, it would be a very low number. It's 3 times 5 times 7 times 1. No, that's 7 to the 3rd power. Super high number at the... This is going to be pretty straight down. So not quite over there. So that's an idea of what the graph would look like. Again, I'm not going high enough here. I probably should have changed my scale. And I'm not going low enough there. I love online graphing calculators. They can get these really quick. But this is how they give it. So that's what you need to know. Alright. Here's another one. This one doesn't have a multiplied factor. Let's see what its power is. Multiplicity of 3, or 3rd degree here. And I think I might have covered a 2 there. Yeah, there's a 2 there. That's hard to see. Got another color marker. And that has a 2nd degree on it. So here we have a total of 5th degree. It's positive, and odd degrees normally go down on the left and up on the right, with some sort of swirling between. So we know this because it's an odd degree. The degree is 5, and it's positive. This is our end behavior. So that's a good thing to look at, to know what your graph is going to look like. So after you find those zeros, you know which direction it's coming into those zeros without plotting a bunch of points. And then if you do plot some points, you should know what to expect where they come from, which is actually really helpful. That way if you make an error, you can catch it. Alright, so where are our zeros? There's one at 1. Because if we solve this, x minus 1 equals 0, we get 1. And there's 1, x plus 3 equals 0 at negative 3. 1, 2, 3. Alright, we're going to expect this to be coming in from below, going up and over, back down, and it can't go through here and end up high. If I look at that again, that's a second degree. That's going to bounce off. So we're going to expect something like this here. And this is third degree, so it's going to do something like this here. We can plug in some points to get a little more accuracy on that. For example, if we look at 0 for x, we get negative 1 cubed. That's still negative 1. 0 plus 3 is 3. Negative 1 times 3 is 3. But this one's going to be up to here. So it's going to come down here and bounce. We could get, if we plugged in 2, you can see how high that's going to go there. 2 minus 1 is 1. 1 cubed is 1. 2 plus 3 is 5. So 2, 5. 2, 3, 4, 5. So it's going to go up pretty fast. Out like that. If we plugged in negative 1, negative 1 minus 1 is negative 2. That's 8. 8 times 2 is 16. Oh, this is coming from higher up. No. The bounce is up higher. So, kind of cheating here. That might not be the highest value, but it's going to be pretty darn close to it, because it's generally about halfway in between, and negative 1 is close to halfway in between, so I'll just estimate it there, just for a quick sketch. And going on down this way. And if I needed more accuracy, I would plug in this value and see how low that went. Just depends on how accurate you need it to be. But that is, oh, sorry about that. That is graphing polynomials. Again, notice how the multiplicity of 3, we crossed with a zigzag. Multiplicity of 2, we bounced off. We plugged in points in between to see how high it would go, and just after or just before, just to get an idea of the stretch of the graph. And that's graphing polynomials, and we also did how to find the equation of a polynomial from a graph.